So, hello friends, this is the part of my lecture 2 as the magnetotic methods. So, I think you must have followed part 1 lecture, everyone. So, in this lecture, I will be covering the data analysis, mainly the interpretation, how this survey is going to be used for regional mineral targeting, and the typical 2D resistivity section for the M to cover up empty case studies and how we detect the anomalous conductivity structure and empty inversion modeling. Mainly case study will be going to cover with oil exploration, geothermal zone, so traditional MT methods. And I will be just like lecture series 1, the survey layout and the data logger, I will be giving a brief of this method. So this is myself Devajyoti Shaha with the empty instrument, typical 8 channel. So this is a very important topic for UPSC Geoscientific examination. So let's rock, friend. So in the UPSC Geoscientific examination syllabus, the empty topics is there. You can follow this thing, empty field. So common theory I have already covered in the first lecture. It measures the electrical or magnetic field at the Earth's subsurface. Earth's surface is a passive field. It measures the conductivity of the resistivity structure, and we measure the complex impedance with the tensorial equation and the phase factor. So this is in the matrix form. So we measure mainly the complex impedances ZXX, XY, these components. Very much computational method is required because numerous frequencies are involved and sophisticated data processing is required. So we have long period, we have intermediate period, we have short period electromagnetic waves and their penetration. So like that we can have resistivity as a function of impedance square and as a phase factor phi tan inverse z, and also the tensorial equation in my last slide. So if you see the electrical conductivity range in a log scale, you can see copper is highly conductive, then graphite, iron is there, metallic sulfides are also conductive, seawater is also there, and you can have basalt, diamond, quartz in the low conductivity region is highly resistive. And we generally measure Z, XY, XX, YY. They are called impedance elements. So they mainly measure the dimensionality, means 1D, 2D, or 3D, or the directionality, which is very much required for MT data interpretation. That I will be discussing in my next slide. So for survey layout, you can see. Let me show you. This is the data logger, main data logger. You can see this is the 8-channel data logger. So we'll having 3 magnetic field coil sensor HX, 2 magnet HX, HY, and 1 magnetic field is buried directly to the ground to measure the vertical field component, and HZ. This HX, this is in the XY direction, this is in the north-south direction, and 2 electric dipoles, north-south and east-west direction. So they are connected to the data logger at the midpoint of the cross pattern, you can see. And this is a typical 8-channel empty instrument. All the connection are going as like the schematic diagram. And this is one of the figure of the electric dipole, you can see. And this is a magnetic sensor which is connected to the data logger. So if we tell about the data analysis, the common things is the time series pre-processing steps. Then we convert the time series into frequency domain using several methods, like there will be spectral analysis, there will be remote referencing technique. One instrument will be acquiring the data, and with respect to that other instrument is taking the data, so that T1 and T2 time will be measured, and then remote referencing technique will be followed everywhere. It's a standard method. Another thing, we can have spectra and then impedance tensor calculation, as I told you. We have to define the dimensionality 1D, 2D, or 3D, and the electric strike, geoelectric strike direction of the data set. Several techniques can be used: phase tensor decomposition, mode cycle technique, vertical induction vector, like that. Lastly, our outcome will be the pseudo section of the data, which can give impression about the resistivity variation in the depth and distance as per the tensorial formula. Now we move to our most important part, data interpretation. So we'll be having 1D, 2D, 3D inversion. So talking about 1D, it's a very fast, easy, and they will give always the wrong mainly. So 2D modeling is more reliable, and we should have acquired the data in a profile mode. But sometimes we have 3D effect in the data. So in that case, 3D modeling is very important. That in that case, data should be acquired in a grid mode. That is used to verify the 2D results. So it takes a huge computational time, computational requirement. So this 2D inversion, this is basically. So when you talk about the empty data response from the Geoscience Australia, you can have that this is a resistivity factor, that is mod of z square. So this is the two components, zxy, zyx. The point when these two deviate is called the dimensional is different. If xy is equal to yx, it's the same dimensionality, and this is the phase factor. You can see you can have more larger error bar at the larger periods, might be cultural noise or anything, and it is the typical xy or yx component, how they behave at higher, lower to higher frequency, or the higher to lower frequency regimes. So I will show you some examples of the empty data as a case study. That is the xy and yx apparent resistivity and the phase values. They are measured without editing. I mean, and it is a representative of the profile sites. So you can see the no anomalous behavior at the intermediate period, but at the long period, the low frequency, they're having larger error bar. In that case also, in that site number 45 also, site number 47, these are the long periods. They are representative of the cultural noise, and low frequency means low solar period activities. So very poor side, and also very higher frequency data are also showing some errors. This error is there in there, so this site has to be, this proper data interpretation is needed in that portion also. In that portion, this is just a raw picture to show you the glimpse of how xy and yx varied with frequency at different sites. This is the standard paper with the given with the reference. And the modeling, so we cannot have an accurate estimation of the physical parameters from a set of data. So if we carry out 2D inversion, which is non-linear, this is non-unique, and there may be an infinite set of models which can be found, and then it's the unstable problem. So we generally need regularization to find a better solution. So you can apply prior information, geological and the geophysical input is always there. So now we shift to the case study example in one of the empty 2D resistivity section along Dharwar Craton. So by carefully looking at this picture, you can see there is no resolution in that up to 20 to 25 kilometer. So we can tell this is due to the lack of high frequency data. This portion cannot be resolved. It has been generated from the joint inversion of the empty and the tipper function, which is I have showed you in my previous slide. And there is a surface geology. Surface geology is along there in the profile. So different types of geology. This is a geological boundary. So you can see that the C1 to C9 structures, that is having a 100 to 1000 ohm meter resistivity or the higher conductivity. This has been originated in the crust, and they extend further deep into the mantle lithosphere. They are labeled as C1 to C9. And in the shallow lithosphere structure within 90 kilometer, they are interspersed C1, C2, C3, C4 to C7 with a highly resistive background. You can see this RO, R2, R3 around 3000 to 10,000 ohm meter. So in the background there's a higher resistivity, and we can have some conductive to moderate conductivity structure, higher conductivity. And the electrical lithosphere asthenosphere boundary is also mapped from the MT model. You can have a picture. So this is the whole structure that have been uh, depicted by 2D resistivity MT model. Now you can see the Auslamp picture, the case study of Pan Australia MT survey. So in the left you can have some 2D resistivity structure with some conductive C1, C2, which is from lithosphere to mantle that are extending deep into the mantle, and some highly conductivity structure at 20-kilometer depth. In the right side, you can see the lower resistivity zone, means high conductivity zone at around 37 kilometer of depth. They are generally associated with a gold deposit correlation, the deposits of gold that has been, overlaid on this low conductive, higher conductivity and lower resistivity zones. So this is one of the case study in Australia. This one is white portion is the sedimentary basin, green one is the alkaline volcanics, and these are typically the gold deposits. And most gold deposits are falling onto the lower conductivity, higher conductive zones, as by this is the correlation. So reference. Now we can have application of multi-scale magnetotelluric data for mineral exploration. One of the case study from northern Australia. So in this, the case study is going on within this study area zone, and with the deposits, the typical data is collected here at the Auslamp sites. This data has been collected in there. So if we have a moderately lower to lower resistivity zone in that portion, this is a copper deposits are there, different types of deposits are falling in that. So very important thing is that the MT is used for oil exploration. So this is a volcanic Deccan Trap, this is a Mesozoic sediment. So there is a large resistivity contrast, maybe there for volcanic rock and sediments. So seismic method can delineate a low velocity material layer. So MT, in that case, MT can be bigger studies between the volcano. So in that, so we have the drilling result that showed the existence of 2 kilometer sediments below 1.5 kilometer thick Deccan Trap in this figure. The MT method proved to be very useful, which has been validated using the deep drilling. This is at Lodhika and Latur, Maharashtra. So this is a 3.5 kilometer of deep drilling has been done in that case. So it is a very important thing. MT can be used for oil exploration when there is a sediments below the Deccan Trap, and below that there is a basement. Very interesting fact. This is one of the very important. Now when we used MT study for the deep crustal survey, like there are many MT studies are carrying out along the profile modes. So in the profile C, from shallow to deep crustal depths and along some traverses. So this is one of the traverse in Deccan Traps from near surface to the 60 kilometer of depth. It is showing anomalous conductive features, which can be attributed to the presence of fracture or the rift zones C1 to A to F. And this 1 kilometer thick top surface, this corresponds with a moderately conductive structure. This corresponds to the Deccan Trap, and there is a followed by the high resistive crust, and the thickness of is about 30 to 40 kilometer. And this crust is dissected by narrow conductive structures, that A, B, C, D, E, F, which may be attributed to the buried drift structures or the fracture zones, as I have already denoted. So this is a typical MT survey case study for deep crustal survey. Now MT can also be used for marine survey. Marine MT instrument has been used at the Gulf of Kutch. This unit measures two electric and two magnetic compared to three magnetic, and they are mutually perpendicular to each other. And there will be low noise and low impedance silver chloride electrode through which electric field is picked up. And there will be two magnetic field corresponding to magnetometer coils, which is cased inside high pressure tubes, and they're attached for two unit for picking up magnetic field. So outcome is the layer of 1 kilometer thickness, then followed by 2 kilometer sediment thickness of Kutch region, our study area for marine magnet, MT for marine studies case study. The reference is given. Now MT, you can see there are some 3D resistivity model or depth slices at 2 kilometer, 5 kilometer, 10 kilometer. Some nice some very high conductive zones are nicely portrayed along these depth slices at different depth. In the vertical section, they can show up to 40 kilometer depth along three denser transits. Now MT is also very important for the Bakreswar Geothermal region, which so MT and radiomagnetological and magnetological method were carried out in this Bakreswar Geothermal region, covering 330 square kilometer area. So you can see that it picked up highly anomalous structure in the western part of the survey at a distance of about 12 kilometer. So an AMT result, this locates the shallowest depth of the conducting zone, and it's a very low, I mean, resistive value 100 ohm meter at very low depth 2.7 kilometer. And right side is the MT result. It can show the depth extension of the 2.7 kilometer up to 28 kilometer, because this is a low frequency data, this is a very high frequency data. So these are the typical case studies in the Bakreswar geothermal region using MT and the AMT survey. So there is a recent advances in the magnetotelluric for regional mineral targeting. So this is one of the references: porphyry copper deposit, some foliation, copper mineralization body, and this is a copper ore body at a low conductive zone. So we can integrate this MT data with other geophysical or geochronological data set. So then we can identify the anomaly that is associated with the mineral system, even in the unexplored area. And enhanced 3D modelings are very much important. They can improve the accuracy of interpreting the geological structures. These methods, they allow for the better resolution of the electrical anisotropy and the heterogeneity. These are very important for mineral deposits. So conclusion is there. There are very much recent advances in the magnetological studies that have revolutionized in the mineral exploration, and they can provide high resolution of the subsurface. And we can integrate MT with multi-parametric dataset like gravity, magnetic, electromagnetic, geochemical, geological data, which can enhance the accuracy and efficacy of the mineral targeting. And this future of MT technology, they can hold promise for innovation and discovery for the mineral exploration. It's one of the representative features of different layers that can be joined and can be used in conjunction with the MT survey. So this is my channel, so you can share, like, and follow it if you, and definitely I request you to turn on the bell notification icon to get all the updates. Thank you to follow my lecture with patience. This is my channel, Physics and Geophysics Learning. Thank you very much.